Thank you for joining us on Synthesis Workshop. On today's Research Spotlight episode, we're joined by David Konrad. David earned his bachelor's degree at LMU Munich and carried out his bachelor's thesis in the group of Professor Dirk Trauner. He subsequently completed a number of research internships at the University of Ottawa, UC Berkeley, and LMU before completing his master's thesis in the LIST group at the Max Planck Institute. He then came back to LMU to complete his doctoral work in the Trauner group, which focused on the work we'll be hearing about today. After his doctoral work, David became a postdoc in the Kravit lab at Scripps, and subsequently worked in the Hook group at LMU before becoming a junior research group leader in LMU Munich's Department of Pharmacy. And from there, I'll hand it over to you, David. Thank you very much for joining us today.
Thank you, Matt, for the invitation. I'm really excited to present our concise synthesis of tetrodotoxin today, which was the main project of my doctoral work in the group of Dirk Trauner. Now, let me start by giving you a brief introduction on our target molecule. Tetrodotoxin is probably best known as the poison of the pufferfish. It has an LD50 in humans of 10 microgram per kilogram, which makes it one of the most lethal non-proteinaceous poisons with low molecular weight. Its bioactivity makes it an indispensable probe in neuroscience. It occurs in many phylogenetically unrelated terrestrial and marine animals. And apart from the pufferfish, this is, for example, the Californian newt, the blue-ringed octopus, or the horseshoe crabs. Apart from tetrodotoxin itself, it occurs with more than 28 natural derivatives. Tetrodotoxin is presumably produced by symbiotic bacteria such as Vibrio and accumulated by immune hosts as offensive or defensive agents. But to date, its biosynthesis and ecological role remain an enigma. On this slide, I've drawn tetrodotoxin from two different angles. The structure of this molecule is characterized by a high density of oxygen and nitrogen functional groups. And the key structural elements are the characteristic dioxyadamantane core, which is appended by a 6-membered guanidinyl hemiaminal. Tetrodotoxin furthermore contains 9 contiguous stereocenters, including the sterically encumbered alpha-tertiaramine and the sterically encumbered tertiary alcohol. It actually only contains one carbon atom that is not oxidized. Now, if you strip away all of the heteroatoms, you see the simple carbon skeleton, which is a cyclohexane that is appended by 2 C1 segments and 1 T2 segment. And this further highlights the structural complexity of the molecule, which makes it so challenging to synthesize and, at the same time, a celebrated target in synthetic chemistry. Before we started planning our approach, we carefully studied the literature and found that almost all prior syntheses established the cyclohexane core early and added the functionality step by step. For example, Kishi and Sato started from 6-member building blocks. Kishi used the benzene derivative and Sato used mu-inositol. Dubois and Isobe formed their carbocycles at an early stage. Dubois used carbene insertion chemistry and Isobe used the Diels-Alder reaction. Now, what we learned from their syntheses is that the requirement to adjust the stereochemistry and the oxygenation pattern on the sterically congested cyclohexane cores could result in an increased step count. This is why we have decided to install the full oxygenation pattern on a linear precursor that is then cyclized at the later stage of the synthesis. The alpha-tertiaramine on the C8A carbon was typically installed via CN bond formation, which must overcome considerable steric hindrance. Several methods have been implemented to address this challenge, such as an intramolecular nitrogen transfer, and this was done via a Beckmann rearrangement in the Kishi synthesis, via their signature nitrine insertion chemistry in the Dubois synthesis, and via an Overman rearrangement in the Isobe synthesis. Sato, on the other hand, relied on an intermolecular nucleophilic substitution, which used an A-side anion and a highly reactive electrophile. Now, to circumvent this challenge, we decided to introduce a nitrogen moiety as an imine-type structure and establish the alpha-tertiaramine through an addition of a slim carbon nucleophile, so via a CC bond-forming reaction. Our ultimate retrosynthetic analysis is shown here. While it is not the exact retrosynthesis that we devised at the beginning of this project, it still captures the essence of our early plan. If we disconnect the spontaneously forming orthoacid and guanidinyl hemiaminal from tetrodotoxin, we obtain tetrotoxinic acid. From this structure, we cleave the guanidine and trace the C9-C10 hydroxy acid back to an alkyne moiety. Now, the most central retrosynthetic step that we made was to transiently connect the C4A amine to the aldehyde oxygen to generate an isoxazolidine, which is the retron of a 1,3-dipolar cycloaddition. From here, the C2 segment could be installed through an addition into the imine of the corresponding isoxazoline. By disconnecting the Huisgen cycloaddition, we obtain a nitroaldehyde, which is the product of a Henry reaction. This aldehyde can be traced back to two starting materials, a glucose derivative or an aldehyde that can be generated through a Kyoka-Aldo reaction. I would like to start my talk with the latter, because this approach has allowed us to additionally implement the synthesis of the natural product quiet-renewal A, which was isolated from the plant Uvaria quaichovensis. Our synthesis of quiet-renewal A started with a commercially available acetonide containing ester that was transformed into a TBS ketane acetal with lithium HMDS and TBS chloride in HMPA. This compound was then added to cinnamaldehyde together with an in situ generated oxazaborolidinone that acts as both a Cairo-Lewis acid, which triggers an aldo reaction, and a reducing agent that reduces the intermediate oxocarbenium ion. This reaction generates two sterically congested stereocenters, which include the tertiary alcohol in good yield NDE. After transfer of the TBS group with sodium HMDS, we obtain our desired aldehyde. In the next step, we can add alkynyl magnesium chloride, which proceeds via a 5-membered gram-chelate transition state, and the resultant alkoxide can be benzoylated in situ. From here, we dihydroxylate the alkene, reduce the alkyne to the corresponding alkene using Lindlar's catalyst, and cleave the diol with sodium periodate to obtain an aldehyde. Another diastereoselective Grignard addition establishes the C3 stereocenter and sets the stage for Grubb's metathesis. TBS deprotection and selective benzoylation gives quiet-renewal A, which we have dubbed the natural product that looks like a synthetic intermediate. And this compound shares 3 stereocenters with tetrodotoxin. When we wanted to use the chemistry developed for quiet-renewal A for our tetrodotoxin synthesis, we had to adapt the protecting group scheme. So after the Grignard addition, we deprotected both silyl groups in the same pot by addition of aqueous phosphate buffer and TBAF. After a dibenzylation, this substrate is again subjected to the dihydroxylation, Lindlar reaction per iodate cleavage to give the aldehyde. In contrast to the Grignard addition, a Henry reaction with tetramethylguanidine at low temperature proceeds with the opposite diastereoselectivity and gives the desired C8 configuration as the major product with a 3 to 1 DR. With this compound in hand, we could finally perform the key 1,3-dipolar cycloaddition to give the fully oxygenated cyclohexane core of tetrodotoxin. To perform this reaction, it was absolutely crucial to use catalytic amounts of base and to stop the reaction at 35% yield. This allowed us to limit decomposition as well as the formation of side products, and we could isolate the product along with the majority of the starting material. Even though the cycloaddition was successful, this reaction yielded the undesired configuration at the C4A carbon. If we increase the reaction time or the amount of the triethylamine base, we increase the propensity for a retro-Henry reaction, and our product is converted to the corresponding phenyl carbamate. Although the carbamate group could be deprotected, the yield for this two-step process was very low. But remarkably, this investigation allowed us to confirm the stereochemistry of our oxygenated cyclohexane using X-ray crystallography, since the carbamate was a crystalline solid. Since our synthesis yielded ample quantities of the undesired C8 diastereomer, which decomposes when subjected to the cycloaddition conditions, we were looking for a method to recycle this building block, and we found that the alcohol could be efficiently eliminated using methane sulfonyl chloride and triethylamine. Since we have used the Kramfek-Ahn model for diastereoselective additions quite frequently in this synthesis, we realized that we could add lithiated para-anisyl alcohol to this nitroalkene with complete stereoselectivity to give the desired C8 configuration. The transition state was confirmed through computations from our collaborators Ken Hauk and Nina Strassner. Quite remarkably, we found that the protected C8 alcohol enabled the cycloaddition with significantly improved yields, and the PMB group could be cleanly removed using steric ammonium nitrate. At this point, the stage was set for our next key step, the formation of the alpha tertiary amine. It turned out that our retrosynthetic considerations were spot on, and this reaction worked very well for lithiated TMS acetylene. Here, it's worth noting that this addition was significantly aided by the C4A configuration that was incorrectly set with regard to tetrodotoxin. We took this as a win and planned to isomerize the stereocenter at a later stage. As easy as setting the alpha tertiary amine was, as hard was the oxidation of the sterically encumbered C2 segment. We originally planned to install a lactone that is bridged between C8 and C10, which we reasoned could be shifted to the C5 and C7 alcohols to establish the dioxyadamantane core later in the synthesis. However, this translactonization proved difficult since the C10-C8 lactone was unusually stable. This is why we next aimed to form the lactone with the C5 alcohol. When we were planning this alternate endgame, we also realized that the requirement to use the strong carcinogen HMPA as a co-solvent in the first step of our opening sequence puts a tight limitation on our material throughput, which does not leave a lot of room for late-stage reaction tests. This is why we next optimized an alternative opening sequence that enables the generation of decagram quantities of the cycloaddition precursor, while our current approach provided about 1 gram. Here, we have started with the commercially available glucose derivative and optimized the first 3 steps that were reported by Sato in the literature, which included a regioselective benzylation, a Swern oxidation, and a Peterson olefination. From this point, our route deviates from Sato's approach through a regioselective reduction of the benzyl acetal to the C7 benzyl ether and a diastereoselective sharpless dihydroxylation protocol to set the C6 tertiary alcohol. Next, we could protect the diol with an acetonide and, in the same pot, perform an Appl reaction to exchange an alcohol for an iodine. Using tibuli, we could trigger a Vassella fragmentation, which installs the linear aldehyde. Addition of nitromethane to the same pot leads to a Henry reaction that proceeds without stereo control. When we found this, we reasoned that we could harness our procedure for recycling the C8 stereoisomer so that we would not lose half of our material. After some experimentation, we found that this reaction could be optimized to enable 3 steps in 1 pot. Here is the mechanistic rationale. Tibuli performs a lithium-iodine exchange, which triggers the Vassella-type fragmentation under elimination of lithium methoxide. Once nitromethane is added, it is deprotonated by the lithium methoxide and adds into the aldehyde. Adding methane sulfonyl chloride and triethylamine upon completion of the prior step directly eliminates the C8 alcohol to give the nitroalkene. As already discussed, the lithiated para-anisyl alcohol adds into the nitroalkene with complete diastereoselectivity. If we now exchange phenyl isocyanate with Boc anhydride and DMAP, we do not require workup and can directly intercept the nitronate anion, which leads to the formation of a nitrile oxide and facilitates the cycloaddition in excellent yield. We realized that 2 pathways existed for the cycloaddition. Either the Boc nitrone performs the cycloaddition and is then eliminated, which is depicted as pathway B, or a direct elimination occurs that generates the nitrile oxide, which performs the cycloaddition as depicted in pathway A. To enable an efficient computation, our collaborators from the Haug lab used a simplified model system, which replaced the benzylic residues and the tert-butyl group of the carbonate with methyl substituents. They found that the direct elimination of the Bock group from the nitrone is more favored by about 13 kcal per mole over initiating the nitrone cycloaddition, which guides the reaction through the nitrile oxide cycloaddition pathway. As already discussed, we can nicely deprotect the PMB group using ceric ammonium nitrate. The subsequent formation of the alpha-tertiaramine proceeds smoothly, and we have optimized the procedure for the TMS deprotection in the same pot by adding an aqueous phosphate buffer solution along with TBAF, which proceeds in good yields. Now, to install the lactone at C5, we needed to deprotect the benzyl groups. To avoid a perturbation of the debenzylation reaction through the nucleophilic C4-amine and C8 alcohol groups, we first performed a double Bock protection. At this point, a new debenzylation procedure was published for the deprotection of complex sugars that use DDQ and irradiation with green light. And although we have unsuccessfully tried to debenzylate our substrate with DDQ and blue light, just changing the LED allowed us to cleanly remove both benzyl groups. Now, this was a remarkable discovery, since many alternative methods were not suitable, due to the alkyne, which is sensitive to hydrogenation, and the acetonide and Bock groups, which are sensitive towards acid. To enable targeting the C5 alcohol, we selectively cleaved the Bock carbonate and installed an acetonide between the C7 and C8 oxygens. Then we cleaved the NO bond with samarium diodide and protected the primary alcohol with a TPS group. Now the stage was finally set to oxidize the C2 segment to a corresponding hydroxylactone. However, we found that the stereoelectronic environment surrounding the alkyne hindered a productive reaction with a broad range of standard oxidation procedures. We reasoned that an oxidation reaction could proceed if the reactivity of the C2 segment is enhanced through a transformation into an enol ether. But our approach to use silver and gold catalysts was thwarted by the substrate's propensity to undergo an undesired 5-exotic cyclization. After some experimentation, we found that the generation of ruthenium vinylidene worked well for our purpose, due to the generation of a species where the electrophilic carbon resides on the terminal position of the alkyne. Since we were already using a ruthenium catalyst for the enol ether formation, we investigated ruthenium tetroxide as a catalyst for the subsequent ketohydroxylation, which provided access to the hydroxylactone with excellent diastereoselectivity. With these two ruthenium catalyzed reactions in place, we were in a position to combine the two methodologies. So once the enol ether was generated, the reaction was cooled, followed by the addition of oxone in a very specific co-solvent mixture. Here the reaction time was crucial to avoid overoxidation, and we could obtain the desired stereoisomer in good yields. On this slide you can see the proposed mechanism in detail. The ruthenium coordinates to the terminal alkyne, which triggers the formation of the ruthenium vinylidene and the subsequent attack of the C5 oxygen on the intermediate. An exchange of a triphenyl phosphine ligand for NHS then enables a proto-deruthination, which provides the enol ether. Once the starting material is fully converted to the enol ether, the catalyst is oxidized to ruthenium tetroxide with oxone, which performs a cycloaddition with the electron-rich alkene. We believe that the chemoselectivity of the second oxidation is due to the increased hydricity of the hemiacetal CH bond within the intermediate. The ruthenium dioxide that is formed together with the hydroxylactone product is reoxidized with oxone and enters another catalytic cycle. With the C5-C10 lactone in hand, we could move on to our endgame. TMS triflate mediated the removal of the Bock group and was followed by a deprotection of the pre-existing TBS group and the transiently installed TMS group with TBAF. Next, we performed an in situ protection of the alcohols with TMS chloride to enable a selective guanide annulation. For the last procedure on this slide, the C4 alcohol oxidation, you can see why we needed to deprotect the TPS group, but were able to use a TMS group. Collins reagent can oxidize TMS alcohols, but not TPS alcohols. The generated aldehyde is directly engaged by the guanidine imihemiaminal. The last remaining challenge in our synthesis was the isomerization of the C4 stereocenter. Remarkably, using a 3:1 TFA water mixture enabled us to remove all protecting groups and perform the isomerization, which presumably proceeds through a formation of a guanidinyl imine and the isomerization to the corresponding enamine. Protonation from the bottom re-establishes the imine, which can now be trapped by either water to give tetrodotoxin or the C9 alcohol to generate 4,9 and hydrotetrodotoxin, which was formed in a 1:1.4 mixture. As already shown by other groups, the mixture can be equilibrated in an aqueous acetic acid solution. In our case, we moved from a 1:1.4 mixture to a 2.9:1 mixture to 4-tetrodotoxin as the major product. In summary, we were able to synthesize tetrodotoxin in 22 steps from a commercially available glucose derivative with an overall yield of 11%. This project wouldn't have been possible without the support of an amazing team. A big thanks to Team TTX, which consisted of Peter Rühmann, Belinda Hetzler, Nina Strassner, Ken Haug, Brian Matsura, Dirk Trauner, and Hiroyasu Ando for their heroic efforts on this project. I am of course also grateful to our funders who made it possible for us to pursue this synthesis. And I would like to thank you for watching. If you want to learn more about our research or have any questions, visit our website or reach out to us on Twitter.
Thank you for tuning in for this Research Spotlight episode, and thank you to David for a very interesting talk. If you enjoyed the episode, you can support us by subscribing and telling your peers about this podcast, and feel free to send us any questions or comments you have. Follow us on Twitter to stay up to date, and see you all next time.